So when it comes to defining the mechanisms that would create the Kubernetes cross-cluster communication, it is essential to define our objectives. And right now, our objective is to support the hybrid cross-cloud deployment in the following way. So the first thing we should keep in mind that there will be a centralized AWS deployment. And so there will be another part of infrastructure that would be deployed per specific cloud. So taking this into account, we need to make sure that our part of infrastructure that is deployed per multiple regions and clouds is capable of communicating with the centralized AWS deployment. As far as this part of the infrastructure will be wrapped into the Kubernetes cluster the same way as centralized deployment, we need to define a way how we can establish the secure and reliable communication between those deployments. So our main objective is so the current use case consists of us being able to support the cross-cloud deployment for Google Cloud Platform and additional AWS regions. So the centralized AWS deployment will remain as it is, but we additionally want to deploy the part of the infrastructure to different AWS regions and different Google Cloud Platform regions. And we need to find out a way to establish smooth, effective, low maintenance, and secure communication among the clusters deployed into these regions. So these are our requirements per this deployment. We want it to be lightweight. And what does it mean it to be lightweight is that it would not consume a lot of resources because we don't want some complicated solution that will provide us a lot of additional features that we might not need. We want to clearly focus on the specific communication between those two clouds. So we want it to be low maintenance. And under that, I mean that we are able to set up it once and have the least amount of efforts possible to keep it running. So practically speaking, we want this solution to have the fewer amount of infrastructure components possible. We don't want this solution to have the storage components. And why is that? Because the more components of the infrastructure our cross-cluster communication mechanism will have, the more of the monitoring we would need, the more of the monitoring alerts, logs we need to observe, the more hassle we have in our monitoring channels, the more maintenance overhead we have. So the fewer components we have, the fewer services are running, the easier for us to observe and monitor how it behaves. Also, why I don't want it to have storage components, because storage monitoring is just an additional unnecessary overhead in our case. As far as we're talking just about communication, network communication cross-cloud, it should not involve any kind of stateful interactions. So the secure. Under secure, I mean that, so we only want, for instance, Google Cloud Platform internal cluster network to be accessed from the AWS internal network and not from anywhere else. So there shouldn't be exposed any kind of endpoints that could be accessed from anywhere else other than these clusters. And of course, we want all the communication that goes outside of the cluster to be encrypted. We want to be encrypted and I would say masked. And why masked? Because I don't want anyone to guess that there might be the hole in this cluster that would allow me to reach the internal endpoints of this cluster. Why is that? Because, for instance, let's say we create an egress rule that would let us expose particular internal endpoint outside of the cluster. So the cluster in the different region can access this endpoint, and someone will be able to figure out the address of this endpoint. Thus, he potentially can access our internal endpoint. Even if we protect the access to these endpoints to be accessed only from the specific IP address, we still need to find out a way to keep it masked so no one can easily find out the internal and expose internal endpoint and try to any attempts of accessing it. And then reliable. And under reliable, I mean that, so it is hard to break the cross-cloud network communication mechanism. And under that, I mean when we're making some infrastructure changes, and let's say changes to the specific resource might have an implicit impact to the other changes, that would, and this implicit impact can accidentally disrupt in any way this cluster network communication, this is the point where we have a low reliability. We don't want to let anyone accidentally break our cross-cloud communication mechanism. And another topic in reliability, I would say it's autoscalability. So when our traffic grows, when the number of requests are growing, we want this cross-cloud communication mechanism to be autoscalable. So any rapid traffic spike won't disrupt, will make it down in any way. So these are the main objectives that we have at the moment. And I would like to have another section that is current knowledge. And the current knowledge will here I just want to express how I currently see this solution and which third-party solutions I know that could be used here. So when it comes to solution architecture, I see it that we might have private ingress. It will expose only specific endpoints. And so I just decided to give the name to this cluster. So the centralized AWS deployment would be our centralized cluster. And the part of the deployment that is deployed per cloud, there will be an extension cluster. So here I would say a private ingress in cluster that will expose only specific endpoints, that will whitelist the IP address only of the centralized cluster. And that will be authenticated by the authentication framework. So it gives us actually 3 layers of security. So the first layer is that this private ingress in extension cluster will have a separate masked endpoint that will only expose some specific endpoints of the extension cluster. This is the first layer. On top of it, it will only allow the access with the IP addresses from the centralized cluster. So if I want to access these external endpoint from my computer, I won't be able to do so because I will be rejected by the IP filter. Furthermore, even if I'll manage to connect to my centralized cluster via VPN from my computer, it would still require me the authentication, some kind of a token or any kind of authentication framework in order to access the cluster. So this is how I envision this solution. Then we will have one-way communication. And why we have one-way communication? Because it would be less maintenance overhead for us. We should only manage the ingress security on the extension cluster, and we don't need to do it in the centralized cluster. The centralized cluster is not exposing any private endpoints anywhere. In case the centralized cluster needs to obtain some real-time data from the extension cluster, it could be done by only subscription mechanism. So thus, there is no other way extension cluster can communicate to centralized cluster other than centralized cluster has subscribed for some specific message broker that is located in the extension cluster, and it can just pull the events whenever extension cluster publishes there. However, when centralized cluster needs to send some data to the extension cluster, it can do it easily by just using the extension cluster ingress endpoints. This is how I envision the solution architecture of this approach. So now I'm expressing my current knowledge regarding the tools that we can use, the different kind of mesh or load balancer ingress tools to set up this mechanism. And just the default lightweight ingress tool that is usually used for Kubernetes load balancer is Nginx. It's a load balancer tool. The only thing that I'm concerned about Nginx that I'm not sure if it has such good capabilities of managing the DNS within the Kubernetes cluster itself. So it would allow us to have the smooth setup of this cross-cloud communicating mechanism. So I'm not sure about these capabilities, if it will be able to actually connect the networks of the extension cluster and the centralized cluster together so they can communicate, and it will be able to help us effectively manage the extension cluster DNS within the centralized cluster. So it won't require us a lot of custom implementation. Another more advanced tool I have heard about it Istio, and I know that it supports cloud communication out of the box. Another tools I'm aware about is Con. It's mostly used for like API-driven mesh system focus. I'm not sure about its cross-cloud communication capabilities because the main objective of Conk is to actually provide the rich tool set for public API management. So I'm not sure how much it correlates about the actually cross-cloud communication capabilities itself. So these are the tools I'm aware about. So the other serverless cloud native solutions, there might be some kind of solutions provided by Google Cloud Platform or AWS that provide us the smooth capabilities of cross-cloud communications and also removing the overhead of managing our mesh system by ourselves that I'm not aware of. So this is the current knowledge about the solution, about its architecture, about which tools could be used, and these are our use cases and objectives. So now it's time to go and research actually which solution architecture and which tool will be the best to meet these technical objectives in order to satisfy these use cases. Okay, so after making a decent research on all of the best techniques and tools that will help us to achieve cross-cluster Kubernetes communication, I have got the following result. So the first things I have researched the tools that could be used, and the first, probably most straightforward and popular tool is Istio, called Istio. So yeah, it just supports cross-cluster communication without public access. It works based on the proxy, so it basically set up the proxy as a sidecar container to each of the Kubernetes pod, and it allows then resolve the DNS address within the cluster, thus routing the traffic accordingly either within the cluster or outside the cluster to the different cluster. It has a centralized control plane, so this control plane helps us to understand how our network works and everything, so we can have the good view on it and also have some kind of a observability there. Yeah, this control pane also has the high availability settings, so it could be set up in the way so it's highly available. So it uses trust model between meshes. The trust TLS helps us actually to work with a zero trust network. So it means that TLS has double site encryption and no one can read the message without the private key. This is the secure thing. Actually, the Istio could be set up as a single mesh or as multiple meshes. So within the single mesh, we have just one unique mesh that can combine multiple networks together. And it just handles internal service-to-server communication within the network. It could be just one network, or we can combine multiple networks together. And the idea is that all the services within the single mesh are interconnected to each other. So there is no restriction to the services within a single mesh to communicate with each other. Yeah, there is like one network spread across multiple clusters with a single mesh. It's one option. The network could be spread across cluster using VPC or VPC peering. We'll discuss it in a second. So yeah, it uses the TLS encryption, MTLS, mutual TLS. It actually serves the encryption and authorization technical objectives that we've established previously. So it's pretty, I would say, good and straightforward approach. So each cluster, it works in the way that each cluster had the east-west gateway for internal communication. So yeah, so just internal communication across clusters. This gateway is private, so it won't be accessed publicly. It's just for internal communication. Yeah, and as I mentioned, each service has access to all the other services within the single mesh. So when it comes to multiple meshes, the story is different because multiple meshes allow us to have more of isolation. Let's get back to our centralized and extension cluster. So we call the centralized cluster is that the centralized cluster where is our main deployment is located, and then the extension cluster is the one that will extend this deployment to a particular region. So let's say we don't want extension cluster to access all of the services within the centralized cluster. In that case, Istio will help us setting up the multiple meshes. So we can have the mesh itself in the extension cluster and then mesh itself in the centralized cluster. And then we will explicitly specify which services from like extension cluster could be accessed by the centralized cluster and vice versa. So we don't have like all-to-all service access. We have a good isolation here. So we just creating a separate mesh to isolate and explicitly define those rules. This was about Istio, and I become really excited about it. I just liked Istio because just so established tool, and it offers a lot of out of the box in terms of observability and functionality. It also offers the external public gateway, so we don't need to set up different public gateway and load balancer because Istio can handle it everything. But I decided to go further and explore a few more tools to better understand what are the alternatives. Another alternative that I found was the virtual kubelet. While virtual kubelet is not something that designed to create cross-cloud communication mesh, but there is still approach to establish cross-cloud communication with virtual kubelet. I mean, cross-cluster communication. And just to recall, so kubelet is an Kubernetes node agent. So in order to be running, it should have nodes, virtual machines, where it runs its compute power. And these virtual machines are running by the kubelets. Kubelets are those agents that run the Kubernetes on the nodes. And the set of kubelet agents that are running on virtual machines actually creates the Kubernetes cluster. But the default kubelet is like a real kubelet. It's not, how to explain it. The default kubelet is runs in a separate environment like virtual machine or physical machine or anything like that. But when it comes to virtual kubelet, we can virtualize this agent in order to extend the capabilities of Kubernetes resources. And so the idea is that let's say in our cluster, we have like 3 nodes, and then we're adding additional virtual node, like using virtual kubelet. That will allow us to create the virtual node that will represent the remote cluster. So we can literally represent the network of the remote cluster within that node. And it means that technically, from the Kubernetes point of view, all the communication will happen within the same cluster. However, this virtual node will allow us to communicate outside to different cluster. The problem with this approach is that it's just more abstract. It's high-level abstraction. It's just lower network level. And it's mostly designed to be used with Kubernetes API to actually use the cross-cluster Kubernetes API. It still requires some network connectivity on the lower level. Well, while Istio could be the network connectivity, well, it's not necessarily true here. Istio also requires network connectivity. However, Istio provides a better high-level interface. And in our case, virtual kubelet will have big limitations because we will be running our clusters in fully managed environments like AWS Elastic Kubernetes Service Fargate and Google Kubernetes Agent Autopilot. So it means that we don't have direct access to our nodes. Our nodes are completely serverless and we just not touching them. We only care about Kubernetes. So I'm not sure if it's possible at all set up virtual in this serverless environment. Even if it's possible, it will be complicated and will have a lot of limitations. So I don't think this approach is really appropriate for us, so why not even continue considering it? And yeah, then we touched topic of the network connectivity. Like all of the mesh solutions like Istio and other, they require the lower level network connectivity. And this is something we need to consider, like what would be our cross-cluster network approach. And there are like 3 main approaches. The VPC peering, VPN, and cloud interconnect. So what is VPC peering? It's virtual private cloud peering. We have our virtual private cloud, let's say it's running on AWS in US East 1 region. And then we have another virtual private cloud that in US East 2 region. So they're in different regions. And so AWS allows us to connect the networks of these 2 VPCs so I can access the services from the first VPC, the services in the first VPC from the second VPC, let's say like that. So we can literally create this kind of a tunnel between those VPCs that will allow us to share the network together. So we literally will have one network with different IP addresses that will interconnect 2 VPCs together. And this is one of the approaches how we can create cross-cluster networks is just by peering those VPCs together. However, this approach is limited because we can only create VPC peering within one cloud provider. So we can only create VPC peering between AWS virtual private clouds. If we want to establish cross-cloud network from multiple cloud providers like Google Cloud Platform, AWS, and so on, this approach will not work. And for that reason, we need to consider different approaches. Another straightforward approach is virtual private network. I think it's pretty straightforward because we all know what it is. It's just easy to set up. You just set up the VPN server, you connect into it, and you have like a private relay through which you operating the communication cross-cloud whenever you want. The problem with the VPN is it's less efficient. It might have higher latency because network should go through multiple endpoints, like VPN endpoint first, and then it should go through the target and so on and so forth. So the speed, the efficiency will be a bit reduced. So it might not be the best solution for the large data transfer. As far as the latency, the one thing, another thing is egress. So if you decide to transfer like terabytes, petabytes of data from one VPC cloud, from the VPC of one cloud platform to the another, from GCP to AWS, let's say, this solution will be expensive because GCP and AWS will charge us a lot on the egress. So we'll pay, I would say, if you're talking about for terabytes data, it will cost for a couple of terabytes, a couple of $100 a month. So it means in a larger scale, in petabytes, it will be like 1,000. So it's really expensive. And if we consider our current use case does not involve heavy data transferring, so that's might be not relevant for us. But if we still need heavy data transferring happening cross-cloud, we should consider cloud interconnect. And basically, cloud interconnect allow us to set up the most optimal physical connection between our VPCs. So we're literally like searching the location of our first VPC, let's say is AWS US East 1, and the second VPC, let's say the Google Cloud Platform US East 2, and we just finding the physical data center location, physical broker who will be between those networks and can create the most optimal high-speed connection. So the traffic between those two VPCs will not reach the public internet. It will go by the private physical tunnel. This approach is a bit more complicated to set up and much more expensive. So how it actually works is that we should find some kind of trusted interconnection service, some networking provider. This provider will supply us with the physical interfaces that we can connect to using AWS Direct Connect from the one side and Google Interconnect from the other side. And that way, our AWS service will have direct physical connection. So the traffic that runs out of our VPC will not go through the public egress and public ingress to the internet. It will use the private AWS availability zone gateway to go to our partners, this network partner provider, and then the same way it will go to the Google Cloud Platform. So this solution is expensive. This networking partner that will interconnect us between two cloud providers will charge us like near $1,000 a month for the low scale deployments. So it's really for high scale when we have like petabytes of data, dozens to hundreds of clients. It definitely will optimize us. It's expensive, it's complicated because we need to make sure that all of these interconnections are set up properly. We need all of the monitoring and observability around it to be set up properly. We need to have like duplicate network redundancy. I mean, so in case one connection channel is broken, we can switch to another one. So we just really advanced, complicated approach. However, it's super high performance because the data will be transferred in high speed with low latency, and we won't be charged by the ingress. And the cost we will pay this network provider will be much lower than the cost we will pay for the ingress if we're talking about large-scale data. So I don't think this approach will be relevant for us because right now we're looking for something more simpler, more straightforward, more easy to set up that we can use on the lower scale. And out of these three approaches, we can balance between VPN and VPC peering. So when we need to interconnect between Kubernetes cluster in AWS and Google Cloud Platform, we can just use VPN. Otherwise, if we have two clusters within AWS, we can just VPC peering them. Our VPC peering will be more cost effective. It will be more efficient. So literally, we will receive all the benefits from VPC peering that we have with Cloud Interconnect. But VPC peering is limited to one cloud provider only, while Cloud Interconnect allows us to literally connect to any cloud provider, any data center in the world. So I would say those two approaches, depending on the use case and cloud platform, will be the most beneficial for us to establish the network-like connectivity between the clusters. So let's move forward to the other cluster mesh tool that will allow us to have the cross-cluster communication. Another tool that I have explored is Cilium. It provides a multi-cluster mesh, and it is a completely different tool from all the other tools that exist on the market because of the low-level mechanism of how it creates this interconnection. And it has something they call eBPF based networking. So it's really like low level setup. It's not using proxies like the Istio uses and most of the other solution uses. So it's highly efficient. It's like low latency, high performance communication. It's really good fit for high throughput workloads when we have like huge data. It's much simpler to set up actually than Istio. It consumes less resources than Istio because Istio runs the sidecar containers, runs all of these gateways, all of these proxies. It just literally, the infrastructure of the Istio is much more complicated and it's high performance. So how it works? What are the difference between Istio and Cilium? So Cilium does not have external gateway, so we will need to set up our own gateway like Engine. Cilium doesn't provide us with such a great application level observability. It is more of the tool for the deeper network level observability, and it provides all of the like low level network level optimization. So I would say Cilium is a great tool for someone who is really looking for some advanced low network level optimization of the data transferring. It's mostly focused on the low level. So we can't have ability out of the box from Cilium. It will let us know which of our services in multiple clusters are connected to each other and how this connection works or not. It just mostly provides network level, like how our TCP packets have been processed, so on and so forth. That might not be as useful in our low scale approach. So the deep network level optimization is the main objective when it comes to Cilium. The other tool I have explored, there are actually a couple of them, however here I just added this tool because they are mostly similar. It's called Linkerd. So it basically offers everything the same that Istio. Well, it's not offers everything the same as Istio. It's just the lightweight version of Istio. So it has less out-of-the-box features. It's much more easier to set up and maintain. It's just lightweight, simple. It has decent application level ability. So comparing to Cilium, it has much better application level. Probably not as good as Istio. So it will still require some additional tools integration to have such a good network observability like Istio. But still, for the simple lightweight approach is a decent one. It has much better performance than Istio. It just has, as far as it's less complicated, has less structure around, less proxies, less networking, less services. It has a better performance. The performance still not as good as in Cilium because Linkerd also uses a proxy-based approach versus eBPF-based networking like Cilium does, but it's much more faster than Istio, and it's just a decent approach. So those are the three tools I have explored. I was also keeping in mind another tool that was Conch. I didn't explicitly specified any information about Conch here because I think Conch is very similar to those tools, and it's probably just a matter of taste and use case to figure out what we can choose. So yeah, I'll just make a comparison here of the three tools that we have. So the main pros of Istio, that is all-in-one solution. So we have the mesh that is east-west networking and gateways that provide north-south networking. It means that like we just set up Istio and have it for everything. Istio actually is widely used, so when you just type cross-cloud mesh in Google, you'll probably get Istio one of the first results. Maybe because Istio is owned by Google or supported by Google, that also might be the case. But yeah, because of its support by Google, maybe it gets such wild recognition. It has really broad observability, so it provides the good insights on the network level. Maybe not as good as Cilium, but still good, and really rich insights on the application level. I would say from all the tools I have compared, it probably provides the best observability on the application level. So in all the other tools, we might need to extend it with additional tools to have such a good application level. It meets all the high security standards. So it uses mutual TLS, runs by proxy, like in the east-west gateway. So yeah, just don't have any concerns about security here. One of the cons here is that Istio requires bigger maintenance. As far as this tool, it's really advanced tool. It requires more efforts to set up, more services to run, thus more resources utilizations, and more complicated to set up. So more maintenance, more complicated to set up. This tool is heavy and low performance comparing to other tools. Because of this complicated infrastructure and a lot of networking proxies, it provides lower performance. And also this tool requires like high initial learning curve. It has complicated documentation for people who are unfamiliar with networking, cross cloud communication, everything like that. It might be a challenge to just step in and start using it. It just requires some of the learning curve. Let's now jump to the Cilium. So one of the pros of the Cilium is the eBPF makes it the most efficient tool because it has like network level security and optimization with eBPF, and it's just highly suitable for large data workloads. I won't be exploring eBPF in detail in this video, but yeah, just in abstract way, it's just an approach to make network communications in a more efficient way than the proxy. It also meets the high security standards like all the tools. It's relatively simple to set up and manage, so it's much simpler than Istio. So it's one of the main benefits over here. Then the cons of the Cilium. It is mesh only, so it does not provide us such a rich networking and gateway and functionality like Istio. It requires like additional tools like Nginx for gateway, and it has really poor application level observability. So for application level observability, they might need to find out any other tool if it's possible at all. So this is a really big drawback here. And then let's go to the Linkerd. So the biggest, I would say, the most significant benefit of the Linkerd that it is a lightweight. It's the most suitable for simple solution. It's just easy to set up, really straightforward. It's easy to maintain. It is more efficient than Istio because it's much more simpler. It has really friendly documentation and really low learning curve. So the people who are unfamiliar a lot with networking and complicated cross-cloud communication can just jump into it, figure out how it works, just read the docs and set it. It is a great solution for that matter. It has decent application level metrics. In comparing with Cilium, it has much better application level metrics. In comparing with Istio, might be not as good as Istio, but still it integrates with multiple metric providers, so these capabilities could be extended. And of course, it meets all the highest security standards. All of these solutions support MTLS, so that's not a question at all. So what are the cons here? It's proxy-based like in Istio, so performance is not as good, and for high data workload use cases, it might be not the best fit. It might require some more advanced configuration. It is mesh only, so the same is, it does not provide everything straight out of the box like Istio does, so it requires just an additional tool like Nginx to set up the north-south gateway. It still has not as comprehensive application level observability as Istio, so it just requires some kind of extension. So these are the main drawbacks of the Linkerd. This is the comparison of all those tools. I also combined those comparison into this table, and I have also included the Kong mesh, because Kong is just another gateway networking tool that I've been mentioned previously. However, I didn't done such a deep research of this tool. I just found that it's relatively comparable to the Istio, but maybe less advanced. So that's why I'm included into this table and just create the comparison. So let's go step by step. So ease of setup. I would say the easiest one is definitely minimal config, straightforward. The most complicated one is just steep learning curve and really complex. Like the second easiest, I would say, is Cilium. It's not the simplest because it requires some eBPF expertise, understanding those network packets. It might not be the simplest thing, but it's not as complicated as Istio and Kong. Kong is also like more complicated to set up, but still it has less features, so it's a bit simpler than Istio. Then another important part is ease of maintenance. So Linkerd is a little low maintenance overhead. the simplest one. Cilium is slightly more advanced because it requires some networking expertise, but it doesn't require a lot of infrastructure maintenance overhead. Like for instance, Istio is the most complicated one and requires the most maintenance, the most control. Kong is slightly simpler than Istio, but in comparing to Linkerd, it's still more complicated. Maybe Kong and Cilium would require approximately the same level of maintenance efforts. Then performance. So the first place will go for the Cilium, the second for the third would go to the Kong, and the last one will be Istio. So Istio has the lowest performance, is high overhead, it's just a lot of invoice sidecars and so on. So Kong has this part a bit of more optimized. That's why it's a bit more efficient. Linkerd is the most efficient of all of these proxy-based solutions because of its lightweight nature. It doesn't have a lot of features, a lot of complicated infrastructure, so it's just more simple. And then, of course, we can compare these three solutions to the Cilium because it just uses a completely different network level approach that makes it like definitely no competitive here. So the latency impact, and obviously performance can reflect the latency impact here, as we probably can see that the Linkerd have a really low latency impact. So if we compare it from the within VPC communication and cross VPC communication, we will notice some impact, but would be really low. And of course, Cilium has like minimum impact. It still be noticeable, but even less noticeable than Linkerd. With Kong, we will have some impact, of course. It's a bit more slow, more complicated, and with Istio will have noticeable impact. So I don't know if it's gonna be the use case for us that waiting additional second or two can impact in some way our service reliability. Maybe it's not the case at all, but it's just an expression for us that Istio probably the most complicated and the less efficient service here so far. Then the resource overhead. Istio spin ups a lot of resources, a lot of sidecars, containers. So there are a lot of logs to monitor, a lot of infra to manage. It's really overhead. Kong pretty much the same. I would say Kong might be a bit simpler than Istio because it has less features, but technically it works the same way. So Kong might have the advantage here because it's a bit more simpler. The Linkerd have a really low resource overhead because it's just the simplest solution, the straightforward, has less infrastructure, less features, less everything. And the Cilium probably has the less resources overhead because the least resource overhead because of its network level approach. It doesn't require to manage a lot of proxies and those network setups that needs for proxy-based services, so it has the less network overhead. And then we can compare the observability. Linkerd has some basic observability that provides the basic information both application and network level. The Cilium provides some advanced network level, but really basic application level observability. And I would say that Linkerd has better application level observability than Cilium. I would say Cilium doesn't have it at all. Of course, Istio has the most comprehensive observability on any level. Well, maybe the network level is not as comprehensive as on Cilium. So Cilium still has better network level observability, but Istio is a no-brainer for application level observability. It's probably the most comprehensive one. However, if we just get back to our use case, I don't think it's even relevant to make this comparison right now, because we will be fine with some basic metrics that provides Linkerd, and that's it. And we probably don't need any network level observability, some basic one, that's also it. So I don't know what to say about Kong, but yeah, we just have it a bit less comprehensive than Istio, but still good. Tracing. So in terms of tracing, we have pretty much the same picture, but here the Linkerd has little limited tracing support, so will provide us with some level of tracing, but also we'll need additional tools to make it more comprehensive. And then it's just, I would say it's just built in with Istio and Kong. So multi-cluster support, all of them support actually multi-cluster. It just doesn't matter how they do it. For instance, Istio allows us to create multiple meshes to have more network isolation within our cross-cluster infrastructure. The Linkerd is much more simpler. However, it's also very suitable for basic use cases. So yeah, this is just a matter of these. In regards to the security, I would say they all really secure in terms of that all support MTLS. The only difference is that Cilium has eBPF-based policies, so these are the network level policies that may have additional level of network level of security. We might count it is an advantage, but I'm not sure if it's going to be very useful for our use case when the Istio really provide advanced MTLS policies, so we can have more fine-grained level of security within Istio, while Linkerd still provides some simple policy setup, so we still have a decent amount of like role-based access management and so on and so forth. And yeah, I'm not sure about Kong, but from what I found here, just probably slightly more advanced than Linkerd, but not as advanced as Istio. And yeah, this is just different type of load balancing they're using. I can't say much about which one would be better for us, but I think it just shows us that proxy-based load balancing are less efficient and more complicated, while they probably more flexible in terms of configuration, while the load balancing on the Linkerd, that is actual latency-aware load balancing, is a bit more simpler and more efficient, maybe not as flexible in terms of configuration as proxy-based. And of course, native kernel level load balancing is probably the most efficient. It works on the kernel level, right? But it's probably not flexible at all as proxy-based, so it has like less room for some customization there. I think the scalability here, like we might notice some differences with scalability, right? If we're talking about really high workloads, petabytes of data. But if you consider more simpler cross-cloud communications, I would say all of them scalable, all of them are scaling well, so we should not be worrying about it. Documentation quality is also an interesting part to consider. So for instance, the Linkerd documentation is really excellent, user-friendly, so it doesn't require a lot of deep technical expertise, I would say really advanced technical expertise to just get it and figure out. It's good because when we have diverse team of engineers and like only 2 specialists who specialize in networking, let's say they made the infra setup, and then this infra setup might be maintained also by the other specialists who not as skilled in networking. And when it comes to some understanding of this cross-cloud communication, Linkerd would be excellent candidate here because it's just easy to figure out how it works and what needs to be done, right? Yeah, well, Cilium, of course, has technical documentation. It's really good, but technical because of the nature of Cilium, this optimization, network level proxy, and so on. The Ist has extensive documentation. Of course, it's supported by Google, so definitely documentation is good, but complicated. And complicated because the nature of this service is complicated, while Kong is mostly enterprise focused. All of these tools has enterprise support. I don't think it's relevant. Yeah, just another metric for comparison. And then we can just compare use cases. So lightweight service mesh with basic L7 observability and simplicity is Linkerd. Then the Cilium is just high performance networking with advanced security policies. And Istio is just really feature rich. It's for complicated infrastructure setup, enterprise grade environments where the flexibility in access control valued more than efficiency. So this is the best fit probably for Istio. Then while the Kong balances the feature and simplicity with API gateway capabilities, it's still more of an enterprise solution when the Linkerd and Cilium is more kind of startup solution, I would say. So this is the comparison of these tools, and just comparing the 2 main decisions that we might want to make here. And the first decision is cross-cluster network decision, and then service mesh decision. So on cross-cluster network, I think we can go through the VPC peering within AWS and VPN outside of AWS. This is the most simple, straightforward approach that will be suitable for our use case. When it comes to the cross-cluster mesh, I think the most suitable tool for us would be Linkerd because of its simplicity. It will provide us with all the necessary capabilities, so it will satisfy all of our technical objectives. It will work through all our use cases. I would say it's the only tool that will satisfy all technical objectives, because when it comes to lightweight and low maintenance, the only competitor for Linkerd is still a bit more complicated. So initially I was thinking that Istio is no-brainer, but after making a bit more deep of research, I would prefer more to Linkerd. However, again, this is just a theoretical research. So all I've done, I've just expressed my knowledge here, my objectives, analyzed the best practices, the tools, and make the theoretical conclusion. So this is just for consideration. And probably the main decision will come from practical consideration. And for that reason, I will need to do the proof of concept. I will need to set up the Kubernetes clusters in multiple cloud providers, set up the network interconnection with them and the Linkerd mesh with them, and figure out if this setup would work well for us and it will definitely satisfy our objectives. After this proof of concept, we can clearly state which solution would be the most suitable for us.